Hello there, guys. How's it going? This is Mike Filipski coming at you here with our first video on elementary number theory. Welcome to the course. This first video is just a little bit of a review or just a little bit of a background of some of the mathematical notation that you're going to be seeing throughout this course, as well as some proof-related facts and some proof-related strategies that you're going to be seeing in this course as well. If you have taken discrete mathematics and if you have taken techniques of proof, then this video should be a little bit more of a review as opposed to a brand new background content. So you can probably skip over this video if you wish, although it doesn't hurt to just get those brain cells working once again when it comes to proving things and when it comes to math just overall. If you haven't taken either or both of those courses, then sit down, chill out, listen to this short video about some of the symbols and some of the proof strategies that you'll be seeing used in this course. So there are some special sets that we're going to be working with when we go through this course. The first set, probably the one that we're going to spend the most of our time dealing with, is a set of natural numbers. And these are whole numbers that are positive. So 1, 2, 3, 4, and going all the way up and all the way on. We don't include 0, and we don't include whole numbers that are negative. And this is the set of natural numbers. We typically denote this set with a fancy capital N. The next most common set that we'll work with is the set of integers, or just whole numbers. They can be negative, they can be positive, they can be 0 as well. So any whole number belongs to the set of integers, and we typically denote this set by a fancy capital Z. The last set that we're going to be spending a lot of our time working with in this course is a set of all rational numbers. These are fractions of things, quotients of things, where the top and the bottom are whole numbers, but the bottom cannot be 0. So it's the set of all things of the form P over Q, where P and Q are whole numbers and Q is not equal to 0. We're talking that guy right there. The set of rational numbers is typically denoted by a fancy capital Q. Now, this set of rational numbers contains some notation that you may or may not have seen, so I just want to go a little bit into the various types of notation that you're seeing here. You see that you have a P, and then you have something that looks like a weird E followed by that capital Z. That weird looking E-like thing is used in this context to say is an element of. So P, weird E looking thing, and then fancy capital Z. Mathematically, that's mathematical notation for P is an element of the set Z, the set of all whole numbers. We see that we have stuff inside of set brackets. We have stuff before a big vertical line and stuff after the large vertical line. So open set bracket, A, big vertical bar, B, closed set bracket. What that's saying is the set of all elements A such that B is true. So it's the set of all things of the form, going back to our set of rationals here, it's the set of all elements of the form P over Q such that P and Q are whole numbers and Q is not 0. And that big vertical bar that's in the middle of our set brackets, that's a mathematical way of just saying such that. We have so much symbolism and so much notation because mathematicians are lazy and we cannot write out two simple words. So that's a little bit of an introduction slash background slash review of the notation that you're going to be seeing showing up a lot in this course. Now we move on to some logic and some proof strategies. The most common logical form that we're going to be seeing is the conditional here. Things of the form if P, then Q. And we can symbolize that with P, big right pointing arrow, and then Q. And what we're going to be seeing in some cases throughout this course is how do we prove something of this form? How do we prove if P, which is our hypothesis or hypotheses, there could be more than one, then Q, the conclusion has to be true. So how do we prove this? So you prove something of this form by first assuming that P, all of your hypotheses, are true. Once you do that, you take that in combination with known definitions and theorems that are related to what we want to know, that is to say Q, and we take those definitions and theorems as well as what we've assumed to be true, and we use those to show that Q has to be true. Now, we'll go through these proofs in the notes in this course. It's very, very, very rare, if ever, that I will ask you to, on a quiz or test, to actually prove something brand new. But just know that this is how we do this particular kind of proof, just so that you can follow with these notes and you can understand what is actually going the heck on here. So that's the most common type of logical form that you see in this course. If P, then Q. The next most common form that we'll see in the theorems that we're going to look at in this course is the biconditional. It's saying P if and only if Q, or with more mathematical symbols thrown in. We have P, and then we have a big arrow that's pointing both left and right at the same time, followed by Q. What this is saying is that if P is true, then Q is true, and if Q is true, then P is true. So it's really taking two conditionals and combining them into one with a special circumstance governing that. So how would you prove a biconditional? How would you prove something of the form P if and only if Q? You would start off, one, you would assume P, then take known definitions and theorems, combine that with P to show that Q has to be true. That's the first half of it. Second half is you'll now assume that Q is true. Take what you've assumed now, Q, combine it with known definitions and theorems and just known mathematical facts to show that P has to be true. Once you've shown both of those, you've shown that you have the biconditional. You've shown P if and only if Q. Now, these two things that we just talked about, proving the conditional and proving the biconditional, these are methods of direct proof. There are methods of indirect proof that we can use to prove these kinds of statements or theorems. Mainly, we're going to look at ones that we're going to look at indirect forms of proof that we can use to prove conditional statements here. The first one is by contradiction. And what you do using proof by contradiction is you assume your hypotheses. So you would assume P. You're also going to assume the opposite of what you want to show. You're going to assume not Q. You're going to take those two things that you have just assumed, P and not Q, combine those assumptions with known definitions, theorems, and just known mathematical facts, and you want to arrive at a contradiction. Something where two mathematical facts that you know or you have found out completely contradict each other. Showing that you have arrived at that logical contradiction, you've had two things that just absolutely cannot happen at the same time. Arriving at that contradiction shows that your assumption of not Q is false. And that's what tells us, okay, then Q has to be true. So this is a little bit more of a mathematically symbolized way to say all this. Assume P and assume the opposite of Q, not Q. Show that these assumptions lead to a logical contradiction. Typically, these logical contradictions involve something like X has some particular property, and then later on you find out using your rules of logic and your known statements and theorems, you find out that X cannot have that same property that you just said that it must have. And that's your clear logical contradiction. That says, okay, my assumption of not Q here is wrong, therefore Q has to be true. So that is our proof by contradiction. And that is the end of this video. So these are just some common techniques of proof that we see and that we're going to see being used in this course, as well as some mathematical notation that you're going to see popping up very, very, very frequently throughout this course. If you have any questions or comments, be sure to drop them in the comment section below. Otherwise, until the next video, take it easy.